Hi guys, so this is another part of lecture 13 in which we're gonna quantify the benefit of the follow-up rectifier. We said orally, that we have get benefit or use both of the half cycles, the positive and the negative, and we could invert the negative into positive. So we said that the efficiency, doubled. Okay. But this was just orally, by drawing and, analyzing and stuff. And in that part of the lecture, we're going to prove that in a quantifiable way. We're going to get equation. And from that equation, we say, yes, we get double the efficiency. Okay. So let's do that. And to do that, we basically will calculate the DC output voltage, just like what we did with half-wave rectifier. We know the relation of the V average or the DC output, which is just the average of the signal. And we know the equation, we know the function, it's a sine wave, so we can do it, okay? And again, just like what we did with half-wave rectifier, it was difficult for us to use the constant voltage model. The output of resulted from the constant voltage model. And it was, which is that basically. So this is the output of the constant voltage model. It's not super difficult, but just a little bit, not easy, we can say. Okay. And it's good to use, the ideal voltage model or the ideal diode model for the diode. And this will be the output from the ideal diode model. Okay. So this peak here was Vmax minus 0.7, Vmax over 2, remember, okay? And this is Vmax here. This is now Vmax over 2. This is because of the use of the ideal model. So if you analyze this circuit, this center tape transformer, follow-up rectifier using the ideal voltage model, you will get this red, output here. So from that red output, we're gonna calculate the average value of the output. Okay. So we know that the average value V average or VDC equal to, you take one cycle and integrate the function over this one cycle. So the cycle is 2 pi, and basically this will be theta, and this will now is V of theta. The output of theta, we can say. The output of theta, I'm sorry, the integration from 0 to 2 pi, the output of theta d theta. The integration, of course. Okay. So that's basically equal to 1 over 2 pi. Then the output has two functions here. So from 0 to pi, it's a sine wave. So from 0 to pi or sine theta d theta. But remember the maximum value. The maximum value is V maximum over 2. And since it's a constant, it can go out of the integration. And we can just make 1 over 2 pi is a common factor. Actually, V maximum over 2 is also a common factor, but let's keep it for a moment. Plus, now what is the relation of the output here between pi and the 2 pi? Remember the input was like this. This is basically sine wave from pi to 2 pi. So sine from 0 to pi is positive. And from pi to pi, from pi to 2 pi, it's negative. So here, this is not a sine. This is minus sign. So the function between pi and the 2 pi, this is basically minus sine wave or minus sine theta. Of course, multiplied by V maximum over 2. So plus V max over 2 from pi to 2 pi sine theta d theta. Okay. And we can, of course, it's minus. So we're going to change the relation in between here by this to minus. So this will be minus here. One may say this integration will cancel. No, because basically this is from 0 to 2 pi, and this is from pi to 2 pi. So they will not cancel each other. Okay, as we will see now. So basically this is equal to 1 over 2 pi, and we can take V maximum over 2 as a common factor. And now let's calculate this. Sine theta d theta from sine theta, the integration of sine theta is minus cosine. So minus cosine here, or minus 1 multiplied by cosine theta. And remember, from 0 to pi, we're gonna make the substitution for the integration limits afterwards. Minus. Again, sine theta integration is minus cosine, and there is a minus, so this will be plus. Okay, so cosine theta, and now the limit is from pi to 2 pi. This is equal to V max 2 pi, 4 pi. Because we have here 2 and here is 2 pi. Then minus 1 multiplied by cosine pi, which is minus 1, minus cosine 0, which is 1, plus cosine 2 pi, which is 1, minus cosine pi, which is minus 1. So this will be plus 1. V max 4 pi. And let's now reduce this. So this will be minus 1. Let's do that with red. So this is minus 1 is minus 2. And minus 2, and here we have a minus, so this will be 2. So this basically will reduce the 2. And this is also 2. So this will be multiplied by 4. Okay, 4. So 4 will go with 4. So basically this will reduce to V maximum over pi. This is the VTC or V average. V maximum over pi. Okay. So the average, this is the average or DC of the output. Okay. That's very good. One may say this was basically the one we get with the half wave, and that's right. That's absolutely right. But remember, this is 1-to-1. So if the transformer ratio is 1-to-2, this will be, for example, 2 will be 2 V maximum over pi will be doubled. So this is with N1 or N primary to N secondary equal to 1-to-1. Okay, 1-to-1. So in general, for any ratio NB or NS over NB, N secondary over N binary, VDC will be equal to NS over NP V max over pi, yes. I mean, if the relation is 1-to-2, I mean the secondary term is doubled or double the primary term, okay? It will be 2 V max over, which is double, the half-wave rectifier. If it's 3-to-1, it will be triple and so on. I mean, it's controllable, and that's good, of course. Okay, that's basically, the DC output in the center tape. Now let's do the same for the bridge rectifier. Okay, again, we're gonna use, the ideal voltage model with the constant voltage model. This maximum here is V maximum minus 1.4. There is no V max over 2. It's just V max over. And again, this is 1-to-1. Of course, this can't be controllable, but I'm doing the base case, 1-to-1. If you use the ideal model, this will be just V max. Just V max. So let's do that. So again V average or VDC is equal to, again we're gonna integrate from 0 to 2 pi, 0 to 2 pi, and this is theta here, and this is pi. So we have here 2 pi, and the relation here is V output of theta. It's a function of theta, because basically when theta changes, V output changes. So here at theta equal to 0, it's 0. At theta equal to pi over 2, it's V max. Okay, so it's a function of V max. So the integration from 0 to 2 pi, V theta d theta. Okay, that's equal to 1 over 2 pi. And again, we have two relations. Let's start from 0 to pi. From 0 to pi, this is just a sine wave, just like this guy. Just like the input, I mean. So, and with V maximum, not V maximum over 2. V max 0 to pi sine theta d theta plus V max again, and the integration from pi to 2 pi. What is this? This is minus sine theta, because basically sine theta here from pi to 2 pi is negative, and that's positive. So this is minus this thing. This thing is sine. Okay. So sine itself, sine theta is positive, will give you positive value if theta between 0 and pi. And the sine theta will give you negative value if theta between pi and 2 pi. Okay. So this is basically positive. So that's basically minus sine theta. Okay. So here we have sine theta d theta. But this sign will be negative. Let's do it even with red to make it very clear to you. Okay. Let's continue. So it will be basically the same. There is no change. 1 over 2 pi, and we'll take V max as a common factor. Then the integration from 0 to pi sine theta, this is minus cosine, minus 1 multiplied by cosine theta from 0 to pi, minus again the integration of sine theta is minus cosine, minus with minus will be positive here. I'm gonna change this to a positive. So cosine theta this time from pi to 2 pi, and these are not equivalent. You cannot take this with this, no, because this is the integration from 0 to pi, and this is from pi to 2 pi. Yes, they are both cosine, but the cosine itself is function of theta. Okay, so this was V max over 2 pi minus 1 multiplied by cosine pi minus cosine 0. Cosine pi is minus 1, minus cosine 0 is 1, plus cosine 2 pi is 1, minus cosine pi. Cosine 2 pi is 1, minus cosine pi. Cosine pi is minus 1. Minus minus will be 1. Positive 1. Let's again simplify this with red. This is minus 2. And here we have minus 1. So basically these two together will give you 1. 2, I'm sorry, 2. Because minus 1 multiplied by minus 2. And this is 2. So this is basically 4. So let's go back to our normal color. So this is equal to V max over 2 pi multiplied by 4. 4, 2 will go by 4 and give you 2. So this is 2 V max over pi. This is the DC in case of bridge rectifier. So this is the bridge rectifier DC. In case of NS or NB to NS equal to 1 to 1. So with the same turns ratio, the bridge is double, with the center tape rectifier. So basically, you will not find center tape. It's better always to implement the bridge rectifier. Okay, it's really beats that design, which is a center tape. But the center tape is a normal evolution. I mean, if you have the idea of the half wave rectifier, okay, and you could do the half wave rectifier and invent it, then the second step, the second phase the most or the most simple circuit to fake a full wave is something out of the half wave. And if we go back to the lecture of the center tape, we can find that it's basically two half waves rectifier. Okay, so that's why this is the normal evolution, we can say. But of course, the bridge for rectifier, it's superior. Really, it is superior, or much better than the center tape rectifier. Okay, but the center tape rectifier as an idea has other implications or advantages with bridge. So we can use bridge with the idea of the center tape transformer to produce negative and positive DC at the same time. So with the input EC, you can have sustainable output DC positive and another sustainable two outputs at the same time for two loads. Okay, one positive and one negative, based on the idea. It's really good idea. Okay, but by itself, the bridge can beat it. Okay, it has many advantages. Okay, guys, so this was basically how to calculate the DC output in the full wave rectifiers that we studied, the bridge and the center tape, and see you in the next video. Bye-bye.